All right. How's everybody doing?
Great. This is so you can hear us clapping that you're here.
Nice. Thank you. Thank you very much. And I see some action in uh, chat. This is nice. Keep them coming. Uh, I'll be paying more attention to the chat as well. But just in case you've got a question and I sort of overlooked the chat, please feel free to interrupt me at any point. Uh, I'm thinking of this lecture as more of a conversation and rather than just like one-way thing. This is also because quantum simulation is re kind of difficult topic because it requires knowledge from so many distinct fields. So it's essentially accessible to mostly graduate students. At least you need to have good background in quantum mechanics, quantum computation, good solid mathematics background, and then you need to know some quantum algorithms as well. So you can just imagine my predicament when I was like, okay, I'm gonna have to explain this to high schoolers. I'm gonna try, which is why I've included a lot of quantum computing memes. Hope you would enjoy it. And the strategy would be we would start. Let me just minimize this. We would start a little bit of the historical context, and then we would again discuss quantum computation, which hopefully you've had some introduction to in the past week or so. And in the third section, we would discuss how do you use quantum computation to do quantum simulation. Okay, quantum simulation is going to be one of the most promising applications for quantum computation. In fact, if there's uh, any hope for any application, then quantum simulation will be one of the first things to be implemented. Okay, and before we get into what quantum simulation is and why we are interested in that, let's go through a little bit of historical context where where's my cursor? Okay, there you go. Okay, so the field of quantum mechanics itself started with Max Planck in 1900. And as we know, the nature at microscopic scales behaves very differently than what we are used to. And now the credit of quantum mechanics mostly goes to Max Planck for his introduction of the concept of the energy quantization in year 1900. Now, this is something that I find it really fascinating how history could be influenced like much later. At the time, Max Planck had absolutely no idea what he was doing. In fact, he proposed the concept of um, this energy quantization in a completely different context, where he was interested in a problem in thermodynamics, which is a study of heat and temperature. And they had like some experimental results, and they were trying to explain those results. And while doing so, uh, he said, oh, you know what, if you assume that the system is comprised of like these tiny oscillators, and you assume that there's a minimum of the energy that they could have, and it's not a continuum, then you could explain the data. Now, this is also like demonstrated in a letter that he wrote in 1931, where he said, the introduction of energy quanta was a purely formal assumption, and I really did not give it much thought except that no matter what the cost, I must bring about a positive result. And the positive result he was referring to was the explanation of the data with the theory. So it's really fascinating that even though the credit for coming up with the foundations of quantum mechanics goes to Max Planck, he himself did not have any idea what he was doing. And I'll come back to it a little bit later, how there's another peculiarity about this trend in scientific community that I particularly find very fascinating. So once Max Planck had his energy quantization idea, I'm having some tech trouble, but oh yeah. So this is Max Planck before quantum physics, and I'm hoping that you guys are laughing. I was. Anyway, so why do I have it twice? So now we have Einstein. So in the year 1905, what Einstein did, he said, you know what, I'm going to just take Planck's results, and if the energy is quantized, he applied that result to explain the photoelectric effect. And up until then, this photoelectric effect, which is basically related to when a light shines on a metal, then it can eject few electrons, and that in fact is a function of the frequency rather than the intensity. Okay, so he said that the minimum frequency could be explained by using Planck's results. Again, he didn't think too much what Planck's results implied. And again, I don't want you guys to focus on what photoelectric effect is, or I don't want to talk more about it, but just know it was another phenomenon that required explanation. And Einstein used Planck's results as a given and said, hey, if this is possible, you could explain the photoelectric effect, right? And again, they're absolutely nowhere close to thinking about quantum mechanics. In fact, even up until I think 20s or middle of the second decade of the 20th century, Max Planck and Einstein again had, they themselves weren't fan of their own results. For example, in 1916, when Max Planck was recommending Einstein's membership to Prussian Academy of Sciences, he, in the letter of recommendation, he wrote, there's hardly one among the great problems in physics to which Einstein has not contributed. That he may have missed the target in his speculations, as in his hypothesis of photons, cannot really be held too much against him. It is not possible to introduce new ideas without occasionally taking a risk. And Einstein went on to win a Nobel Prize in 1921 for his explanation of the photoelectric effect. And then, starting from Einstein's results, in the next 2 decades, there were so many more experimental phenomena which were explained using quantization, and many of these properties which would sort of result from what Planck started. And around the middle of the 3rd decade was when Erwin Schrodinger proposed his wave equation in 1926. Okay, and he was the one who sort of proposed that, you know what, for each particle or a system, you cannot talk about their position and momentum as you do in classical physics. So hope you guys remember a little bit from your science classes that in classical physics, you have each particle associated with position and momentum. The state of the system is described by describing each particle's position and momentum. Erwin Schrodinger proposed that it's not the case in quantum mechanics. In quantum mechanics, you can only talk about probability of finding an electron somewhere, and you have this thing called wave function, which describes the state of the function. And the particle does not have any position until you measure. So we will talk more concretely a little bit later in the quantum mechanics section, but know that he proposed the equation that governed the evolution of the wave function. Okay, just like in classical physics, you have a particle being described by position and momentum, and you have Newton's laws, which tell you how those position and momentum change. For example, you have second law, which tells you F equals ma, and then you can use the force on the particle to know how the position and momentum is going to change. Similarly, corresponding to each quantum particle or a quantum system, you have wave function associated with that quantum system, and Schrodinger's equation tells you how that wave function is going to change in time. Okay, so this was sort of where things were at the end of the third decade. Okay, and I'm going to come back to one more peculiarity that I mentioned in Planck's section. That peculiarity is most of the scientists who laid down the foundations of quantum mechanics absolutely hated their results. They were only able to come up with these results without thinking too much about their philosophical implications. Both Planck and Einstein and even Schrodinger, they all hated what their equations and their results implied. So when Planck proposed his energy quantization, he wasn't thinking about what it would mean 30 years later. Another fascinating thing, he did not even believe in the ideas of atoms and molecules. So that's another crazy thing. When Planck proposed his result, world still was debating whether we have atoms and molecules or it's just continuum all the way. And most of these results were from that time. Schrodinger, the famous cat experiment that I'm sure all of you know by now, the cat experiment, his proposal of cat experiment was his way, wait, I've got a question. How did Planck come up with the work quanta? Oh, yeah, so that's a very good question. As I mentioned, do we have more questions before that? I'm sorry, I'm having a little bit trouble with my computer. Yeah, so what he was looking at was this problem in thermodynamics where I think it was some sort of a graph. Stephen. Yeah, so he was looking at how the temperature, the radiation changes with the temperature. So you have this graph where you have temperature versus the wavelength. So you probably know if you have a material and you heat it up and it glows, okay? And so, and the color changes. Now, color is is correlated with the frequency. So he was trying to explain results in that, in radiation, and he said, you know what, if you assume that the whole system is comprised of these oscillators, and then you work through those, you put a lot of them together and you do their statistical physics analysis, and the distribution you would come up with would then explain that graph. Again, that's going a little bit into details. Yeah, black body radiation, somebody said that. That's perfect. So that's exactly what he was trying to explain, like a problem in radiation. To be specific, he was trying to come up with a better explanation for Wien's displacement law. Okay, and so moving on, the thing that I want you guys to take away from this is how we got more stuff coming up in the chat. 1 minute. After his wave equation, yes. So he formulated his experiment after the wave equation. Quantum. That's a good question. I think I've read about it, but for some reason I cannot remember right now who proposed the word quanta.
I'm pretty sure it comes from Latin, and it means like amount of stuff. Like if anyone speaks a Romance language, quanto, like that, it has the same root. And I think it had to do with quantization means breaking up into smallest finite parts, right? And so he was like, how many of these smallest parts do I have? How many quanta of matter exist in a system or whatever? And so that's quantum mechanics, is the mechanics of the smallest components of matter.
Yep, there you have it. And I think it was Planck, but I'm not too sure. Maybe like that's something that you can just Google it and it should come up. And so Schrodinger, as I mentioned, that the cat experiment was actually his way to argue how ridiculous it sounds to have quantum mechanics. So once he proposed his wave equation, and then people got to think, and they got to thinking about like what it means. And finally, when they realized, oh wait, this could actually imply that a particle could be in two different positions at the same time, two different states at the same time. And then Erwin Schrodinger said, oh, really? And that doesn't surprise you? All people who are proponents of this interpretation of quantum mechanics. And if that doesn't surprise you, let me propose another experiment, which would be absolutely ridiculous. And hopefully you would realize that we need to come up with a better explanation. And that was the time when Albert Einstein wrote to Schrodinger saying, hey, you get it, like how ridiculous this theory is that a cat could be dead and alive at the same time. Why aren't other people getting it? And turns out this in fact is true. Like if you set up system in certain ways, and hopefully you would carry out your learning and realize that that's exactly what the case is, where a particle could be in two different positions, and correspondingly a qubit could be in two different states, 0 and 1 at the same time, until you look. Okay, and then moving on, just if you could give me 1 second. That, yeah, so once you have had the Schrodinger's equation, and after that people started realizing, oh, you know what, let's take the Schrodinger equation and then try to explain a lot of the physical phenomenon that we see in the world. And that's what people started to do. They started explaining the spectra of the hydrogen molecule, and they wanted to learn more things in chemistry. So the underlying theory of whole of chemistry became quantum mechanics, where everything, people were trying to explain everything using quantum mechanics. And that's where this amazing physicist Paul Dirac realized, and to quote him, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws lead to equations much too complicated to be soluble. So he was the first one who realized, even though we understand the equations which govern nature at the microscopic scale. So it's, okay. Jason is taking care of many of the questions, so good job. I'm going to keep going. And Jason, please feel free to interrupt me if there's a question that I could address. So Paul Dirac pointed out that uh, even though we know all these equations, it's just they're too complicated to be soluble analytically. Okay, and even with the advent of the computers in the following decades, they realized that even using computers, these equations are still very complicated. And the computational resources required actually scale exponentially in system size. What that means is if I add one more particle to the system, or roughly if I add one more particle to the original system, then in order to simulate this bigger system, the resources, computational resources required double. So with each additional particle, the computational resources sort of required sort of double. And this is very problematic. And this is where another amazing physicist, Richard Feynman, in 1982, proposed the idea of developing a quantum simulator. To quote him, he said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." The idea was the systems that you're trying to simulate are quantum mechanical in nature. And nature, we know, behaves quantum mechanical in nature. So he argued, why don't you make something that already has quantum mechanical properties and just somehow try to control it? And while doing so, somehow you could also map the system of interest that you want to study to this controllable quantum system, and you'll be able to study it much more efficiently. Okay, and this was after many decades of people trying to understand chemistry using normal computers and falling short on computational resources. And that's where he proposed maybe we ought to build these controllable quantum simulators on which we'll be able to map the quantum system of interest and then study it. And this very vague idea sort of gave rise to the field of quantum computation. As you can see, he didn't provide a lot of details like what sort of controls or gates might be possible, what sort of operations you might be able to do with such quantum simulator. All he said was, we already know that the nature is quantum mechanical in nature. Somehow try to build controls which could have a quantum effect on the system that you're able to control. Okay, and later on in 1986, David Deutsch formalized this idea much more, where he proposed that using quantum mechanics, these are the operations which are possible, and he showed that whatever you can do with the normal computers, classical computers, you will be able to do with quantum computers. Further, he showed that he gave an example of one algorithm, which is Deutsch's algorithm, which I think you guys might have encountered in this QBSCAP. He gave that algorithm as a proof that you could do something better on quantum computers that you just cannot do on classical computers. Okay, and after that, the field sort of took off. People started paying more attention, and we are where we are right now. And so quantum simulation, why do we want to do it? From the science perspective, we just want to learn more about the world. There was this very recent article by John Preskill who suggested that we may be able to develop quantum algorithms for spotting quantum black holes in the lab. So again, you can do really fascinating simulations using quantum computers. And there are people working on developing simulations on quantum computer to study quantum gravity and high energy physics. So a lot of cool stuff going on in there. Hopefully some of you will choose quantum computing as your research work, and you will explore such problems in your PhDs and your undergrads, graduate studies. From the engineering point of view, the hope is we'll be able to develop better materials using quantum computers, because we'll be able to address and solve problems that we just can't address and solve using the classical computers, right? More examples include drug design and secure communications and so on, right? And now we come to quantum computation. But first, I see there
Yeah.
are questions in.
So the question about to what extent is Feynman statements correct? Kind of you could explain this, but basically, when you say on large scales that nature is not quantum, that's what we call a limiting case. Yeah. So kind of do you want to?
Yeah. So the idea is, as per our understanding, nature is quantum mechanical. Classical is the limiting case, where if you put so many objects, then you can show so many quantum mechanical systems together, then you can show that they start giving you back the classical laws that you're very used to, right? So you're talking about one or two atoms, but if you put Avogadro number of them, and then you put more and more. So Avogadro number of them is basically, let's say, 6 grams of carbon atoms. And we are how much grams? So let's say an average person weighs 75 kg or 70 kg. Then you have 70,000 grams, right? So you would have 70,000 divided by 6 into 6.023 into 10 raised to power 23 atoms. And those individual atoms behave quantum mechanically. You put so much of them together, and then they start demonstrating classical physics. Is effect of indeterminism. Yep. A lot of good responses. No, so yes. Okay, Jason already said exactly. Then do we have more questions now? Or should we move on? Okay, let's move on. So let's review quantum computation a little bit more. But first, as I mentioned, how many people feel comfortable with what they've learned in the past week or so? Okay, I'm just gonna move on. It's much easier when I could see faces of everyone, but so moving on. According to quantum mechanics, we've got 3 axioms. So before we talk about quantum computing, that's fair, that's fair. That's fair. Actually, funny you say that it's going to take quite a while to feel comfortable with this, because I definitely have a meme for that. I've saved it for later. Anyway, so quantum mechanics, as I said, let's go back to Schrodinger. He said, again, it's not just Schrodinger, he gave the final equation, but this is the summary of what happened in the first 3 decades. Everything was packaged into a few axioms, which we sort of have to take as given. The first axiom is the quantum state of an object is described by its wave function, which behaves according to Schrodinger's equation. And this is just review from, I think, lecture 1 of this CUBES camp, okay? And you have this wave function, which behaves according to Schrodinger's equation. And then you have a rule which tells you how you can talk about probability of finding the system in a particular state from the wave function. That's axiom 2. the wave function of a quantum object tells you about the probability of measuring a property related to quantum object. So you've got wave function, and then you can talk about just the way you had a particle in classical physics, let's say ball, you could ask, where's the ball? What is the position of the ball right now? And then you could ask based on your Newton's laws and its initial position, and then you can predict what its final position is going to be. Similarly, with quantum mechanics, you've got the wave function. You can ask about the property of a given system, and you can get that property from the wave function. Okay, and then the third axiom is about the measurement. It says how the wave function collapses. So let me just read it. At the time of measurement, the wave function will collapse so that at that instance, probability distribution is 0 everywhere except for the state corresponding to the measurement's result where it is equal to 1. So what that means in the context of, let's say, qubit, if you have a qubit in a superposition, let's say equal superposition, then if you measure it, it just collapses into one of those things, right? So it gives you probability distribution, but when you measure it, you only get to see one of the outcomes. Even though particle could have been thought in two different positions, but once you measure it, it sort of materializes in a single position. And this was one of the things that most of the physicists had a lot of problems with. Even Einstein, till the very end, was very uncomfortable with quantum mechanics. While talking to his biographer, he actually, so he was once on a walk with his biographer. He just stopped while talking about quantum mechanics. He just stopped and looked at the moon and pointed at it and said, "Do you think the moon's not there while I'm not looking?" Turns out, if the moon was microscopic, then you can definitely show that, in fact, that is the case. While you're not looking or measuring the system, the question, what the state of what the position or position of the moon is, that itself is not a very good question. Okay, so you've got these laws, and then you come back to Schrodinger's equation, which is given by I d psi over dt equals h psi, where h is the Hamiltonian. Now this you can think of as some sort of a function which operates on psi, and this is the equation that you're trying to solve. And this is where I think I'm gonna lose some people. So if you've got any questions or if you're familiar, please feel free to ask me as many questions as possible. But you don't have to think too much about like what we're trying to do, what the equation exactly means. All you need to do is, for any sort of system, oh yeah, I mean, you could have that, or you can, many times what physicists and chemists do is just take h bar to be 1. So you work in something called dimensionless units, and there the h bar is just 1. But that's a good question. Yes, that is a derivative. And so what I want you guys to take away from this, what you're looking for are the eigenfunctions of h, okay? And are people familiar with eigenfunctions? So let's see. Tell us lots more about eigenfunctions. Okay, so so eigenfunctions are a little bit easy to understand in the context of matrices. So imagine this H were a matrix. So what we're going to do is, you have this differential equation, and you're going to have to take my word on this, you can turn this differential equation into an algebraic equation which involves matrices. So that's another jump that I'm sure you will learn a little bit later, but let's say you made that jump, now you're dealing with matrices. And if you have a matrix, and if you guys remember, you can have a vector and you can multiply that vector with a matrix, okay? Now, if I have a vector and I apply or multiply that vector with a matrix, and let's say if I get that same vector back, but multiplied by a scalar. In that case, that vector is called the eigenvector of the matrix, right? So in a similar context, yeah, so let me see if this works. Yes, so if I have h, let's say psi, and I get lambda psi, then this is basically my eigenvectors. Does that make sense? And this is my eigenvalues. Psi is an eigenvector, yes. And just the way you guys have learned, psi equals alpha 0 plus beta 1, and you represented it with, sorry, alpha, beta. This was your vector, right? And the Hamiltonian here is a matrix. Yes, exactly. In general, Hamiltonian is a function, but as I mentioned, you could discretize the system and turn it into a matrix. So lambda corresponds to the magnitude of the probability. No, I don't think that's, it's just the eigenvalue. So lambda, in fact, corresponds to the energy. State is not normalized after being transformed by h. It could be normalized. You could write this in a combination of eigenvectors. Okay, so again, we're gonna have a lot of questions. So let's just move on. Like, remember these questions, we can come back and discuss them in a little bit more detail. But to give you a little bit overview of the quantum simulation, I'm gonna have to move. So, now coming back to quantum computation, you guys heard about qubits, their general states. You learned about Born's rules and how you get the probability from the vector psi. And this is just from, I think, module 4 and 5. Does anyone have any questions regarding these? Or I'd like to move on because I really want to discuss a few more things. Got it? Cool. And so you had the state of the qubit, and you have some control operations, which you probably remember are Hadamard, poly X, poly Y, poly Z, and so on. Okay, and then and this is, I think, module 6 or module 7, the multi-qubit states. Now, the multi-qubit states are a vector of length 4, so it's a 4-dimensional complex vector, and the vector is the state psi is given by A00, ket 00, A01, ket 01, so on. Okay, and the 2 qubit gates are specified by 4x4 matrices. Okay, so far so good. Now, then in the same module later on, got it, so good. In the same module later on, we discussed for an n qubit state, the length of the vector is actually 2 raised to power n. And the operations possible in that space will be represented by a matrix of dimension 2 raised to power n by 2 raised to power n. Okay, and this is basically the problem where the dimension of the Hilbert space grows exponentially faster. You add just one more qubit, it grows like the requirements, the computational requirements double with addition of each qubit, right? And this is why simulating on quantum, simulating a quantum computer gets super difficult beyond 10 qubits. And if I could use that intuition and we could come back to quantum simulation, as I mentioned, for each, for physical molecule, you can write Schrodinger's equation. And then I mentioned a jump where you could discretize this Schrodinger's equation, and then you have a discretized version. That discretized version behaves just like qubits. And that essentially is the key, where now you somehow discretize the system. Instead of representing it by matrices of this absurdly big dimensions, you just map the whole system to qubits, right? Now, the dynamics of this quantum system, which were happening, let's say if my system, for instance, had 10 particles, that I would have required 2 raised to power 10 by 2 raised to power 10 matrix to represent the dynamics of that system. But now I could just represent that with 10 qubits. And that essentially is the key, where I sort of get an exponential improvement right away, at least in representing the quantum system. So far, so good. Questions? Okay, moving on.
I have a question.
Yep.
Sorry, it takes a while to get to the button. So you say that this is the second quantization between the Schrodinger's equation and the discretized Hamiltonian, but is the first Hamiltonian, or I should say, is the first discretization when you change from the physical model into Schrodinger's equation?
Yes. So second quantization here means completely something completely different. So sort of ignore that. That doesn't have anything to do with the quantization that we talked about.
So what you're doing is you're basically then you're taking your model and you're just making it discrete instead of saying, okay, these are quantum particles, let's look at them instead as for their discrete values, because we know that these will act like quantum particles.
Yep.
Okay.
Yep.
Thank you.
Yeah, basically you discretize the system, and the discretized version could be mapped individually to a qubit. Again, as I mentioned, there's a lot of stuff in it. Maybe I'm oversimplifying it, but this is something that is hard to convey in a single lecture. As I mentioned, the second quantization refers to the fact that electrons are indistinguishable compared to qubits. And that's like a whole another discussion. But for now, you all are going to have to take my word that this could be discretized. And when you represent this quantum system with qubits, then it's much easier to represent this system compared to classical computers. Just the way if you were trying to represent the state of the qubit, it's almost impossible. And so basically these two impossible things canceling each other. very crudely speaking. Okay, and yeah, so this shows up in most of the chemistry, where all the foundations of all of chemistry is now quantum mechanics. So yeah. And so once again, you have physical molecule. You write the Schrodinger's equation, and on classical computers, if you try to do it, it literally makes your classical computer cry because of this exponential scaling. And this is where the quantum computers come in. Is it or H and A matrices? The capital H definitely is a matrix. And I'm not sure what A are you referring to. Okay, and let's see how much time we have. We're almost, oh yeah, those are operators as well. Yeah, those are operators as well. And then once you got your system mapped, how do you find the eigenvalues? Remember, the problem we're interested in is the eigenvalues of the Hamiltonian. So if you remember a little bit from your chemistry, you've got this atom which has this energy levels, right? And those energy levels are actually the eigenvectors corresponding to the Hamiltonian. So the energy itself are the eigenvalues. So what chemists are really interested in is knowing the eigenvalues of these Hamiltonians, because then they have the energies of the different energy levels in an atom and molecule that they can then use to predict what is the ionization energy, and based on that they could also predict the reaction rates, and they can do all sorts of cool stuff. Okay, and so in order to get the eigenvalues, we have this algorithm called phase estimation algorithm. Again, this circuit may seem very complicated to you, so I'm going to try and explain as much as I can. And just remember, there's this phase estimation algorithm. What it does is, if you have a unitary U and its eigenvector, then it can help you calculate the eigenvalue corresponding to the eigenvector. Now here, by unitary operator U, when I say that, just imagine a matrix. And as I presented to you, the eigenvector and eigenvalue problem just means if I have a matrix, let's say U, then I'm interested in the vectors such that when I act with the unitary U on the vector, I get the same vector back multiplied by a scalar. Okay. And since I'm dealing with, let's say, 50 quantum mechanical particles, which could be thought of as 50 qubits, very crudely speaking, then the space I'm dealing with is 2 raised to power 50, which is where it's very difficult to solve this problem on classical computers. Whereas on using phase estimation algorithm, I can solve it on quantum computers much faster. Does that make sense? And that sort of concludes my talk, where you had this quantum simulation problem where you were interested in finding the eigenvalues of this Hamiltonian H. And then just remember, you could do it using the phase estimation algorithm. Again, there's like a lot of details that I've had to skip, but if you could remember a little bit of quantum simulation, then I think I would be super happy with the job that I did. And may the quantum computers be with you.